Okay, I'd like to talk about another important difference between the particles that make up an atomic nucleus and the electron, which we've talked about before, okay? And to introduce that, I'm going to start by looking at the magnetic moments of these different particles. Hang on one second. Very good. So remember that a particle that has an electric charge, like an electron, and carries angular momentum, like an electron with a spin of 1/2, can be expected to have a magnetic moment, okay? A spinning ball of charge is like a circulating loop of current. It should produce a magnetic field. The magnetic moment of an electron we found was minus 1.0012 Bohr magnetons, where the Bohr magneton is a natural unit of magnetic moment we'll talk about in a second. Protons also can be considered to be a spinning ball of charge. They carry an electric charge, they have a spin angular momentum, and they also have a magnetic moment. Okay, the magnetic moment of protons is given in nuclear magnetons because of their heavy mass. We'll talk about that in 1 second. But it is also interesting to see that the actual magnetic moment isn't an integer number of these nuclear magnetons, but is something more complicated. What's going on there? Finally, it's interesting to consider whether neutrons should have a magnetic moment. After all, neutrons have, although they have angular momentum, they have no net electric charge. So why should a spinning neutron produce a magnetic field? Nevertheless, they do carry a magnetic moment, and here it is, minus 1.9135 nuclear magnetons. This is a strong piece of evidence that neutrons and also protons have an internal structure, so that while the neutron has no net charge, it still might be composed of particles that do carry electric charges and can produce magnetic fields. By the way, just a word about these units. Remember, the Bohr magneton we figured out was a natural unit of magnetic moment for an electron, and it's EH bar over 2 times the mass of an electron. The nuclear magneton is almost exactly the same, only replace the mass of the electron by the mass of the proton, okay? And because the proton is heavier, the nuclear magneton is smaller than the Bohr magneton by about the ratio of the masses. So it's smaller than by a factor of about 1800. As a result, not that it's important in our class, if we do spin resonance experiments on electrons, we find frequencies on the order of microwaves, on the order of 10 gigahertz per Tesla. Whereas for, atomic nuclei, we get much, much lower frequencies in the radio part of the spectrum, around 50 megahertz per Tesla. Any event. Okay, but coming back, it's interesting to see that that the neutron has a magnetic moment and that these values are not integers, okay? So finally, I'd like to leave you with just the modern understanding of the structure of these particles. Electrons are thought to be fundamental particles and point particles, meaning they have a radius which is smaller than can be probed by any collider experiment currently existent. So they have radii less than 10 to the minus 18 meters. Okay? On the other hand, protons and neutrons now are known to be composite particles with an overall size on the order of 1 femtometer, 10 to the minus 15 meters. They're composite particles and they're composed of quarks, with a proton being composed of 2 up quarks and 1 down quark, and a neutron composed of 2 down quarks and 1 up quark. Okay?